Okay, so I hope all of you have joined. So I'm starting up with today's tutorial. Is my screen visible to all of you?
Yes, ma'am, visible.
Okay, so good evening, all of you. Today we are going to discuss about the course Introductory Organic Chemistry Part 2, which is an NPTEL platform course. And the course instructors are Professor Harinath Chakrapani and Professor Niraja Dashaputre from ICER Pune. And I am Simran, your PMRF teaching assistant. So, guys, till now we have taken out 5 tutorials, and the last tutorial was entitled as enols and enolates. So, it was about that. So, if anyone has any doubt regarding the previous tutorial, all 5 I'm talking about, if you guys have any doubt, any query regarding that, please let me know now so that we can take up with today's tutorial. So before taking up, I just want to know that how much people are understanding the tutorials, and if you guys have any doubt regarding these 5 tutorials till now, please tell me now so that we can start up with 6th tutorial. Okay. So anyone has any doubt regarding the previous 5 tutorials? Okay. Okay. If not, then I'm moving forward with 6th tutorial, which is about active methylene groups and aldol reactions. So, guys, previously we have discussed in the week 5 about enol and enolates. So, there we have seen uh, how we can try the reaction with enols and enolates. So here also we are talking about active methylene groups and aldol reactions. So previously also I have taken up these aldol reactions. So today I am just merging up with this active methylene group compounds, and also we will talk up some about aldol reactions. As I have taken it earlier, so we will talking it less. So I'm starting with today's week 6 now. Okay. So moving to problem number 1. So in problem number 1, you have to identify the product of the following reaction. So these are the two reactants, and you have to find the product. So here you have a aldehyde and a dibromoalkene. They have treated it with zinc. So many a times I have told you, when we have added zinc in the reaction, then what will happen? So, can anyone tell me, if we have added zinc in this case, now what will happen? We have gone through these questions in the previous tutorial as well. I think 2 tutorials consist these kind of question, and I have answered it. So,
Reconus reaction.
sorry.
Reconus reaction.
Okay, so oxidative addition it will take between CBr bond, right? So just tell me, which of the CBr bond will zinc insert to? Is it this sp2 hybridized CBr bond, or is it this sp3 hybridized CBr bond? If zinc has to insert, which bond it should be getting inserted? sp2 or sp3?
SP3. SP3.
Sp? Can you just
SP3.
speak some louder? I don't know whether I'm not getting the volume. Yeah. So what did you just say?
SP3.
sp3. Okay. It's now audible. Yeah, sp3 carbon. Why sp3? Because guys, what happens if you have to insert zinc in between cbr bond? That is a oxidative addition step, and you know that sorry, sp2 carbon, this sp2 carbon, this cbr bond length is less than this sp3 cbr bond. So it is convenient for zinc to get inserted between sp3 hybridized cbr bond rather than the sp2 hybridized cbr bond because of the shorter bond length. So it is has having the shorter bond length and having the strong bond. That is why zinc prefers to insert between this bond rather than this sp2 hybridized cbr bond. Okay, so now if zinc is inserted between your this bond, then you are having a znbr species, right? So now can anyone tell me, first step is sorted that you get a znbr bond, right? So it will get oxidatively inserted between this, but now you have another substrate, right? So what will happen next? Can anyone tell me?
Option 1 is right answer.
Option 1 is right answer. Okay. So what is happening next? Guys, I have told you that if zinc is getting inserted between CBr bond, then the zinc has a positive charge because it is a electropositive atom, and the adjacent carbon will be nucleophilic in nature now. So that is why this adjacent carbon will attack onto your aldehyde group, and this way it will get like zinc bromide here, and this carbon will become the nucleophilic carbon. Now this carbon will attack onto your aldehyde, and aldehyde will abstract a proton from the solvent, and you will get this compound as the major one. So option number 1 will be the right answer. So I am just repeating it. First of all, zinc will insert between this CBr bond, oxidative insertion will happen, and after that, as I have told you that it is a electropositive atom, that is why it is having a partial positive charge, and the adjacent carbon is having a partial negative charge. So it is a nucleophilic species, right? So because of the nucleophilicity of this carbon, it will attack onto the electrophilic carbon of the carbonyl of the aldehyde and will give you a alcohol. So is this clear all of you? Why first option is correct one?
Yes, ma'am.
Okay. If it is clear, then just tell me the name of this reaction. What is this reaction? It is a name reaction, right? So what is the name of this reaction? I have told you in the previous lecture. What is the name of this reaction?
Reformatsky.
Yeah, it is a Reformatsky reaction. Whenever you have a zinc which is coordinatedly inserted into between the CBr bond and then it is acting as a nucleophile, then you will say that it is a Reformatsky kind of reaction. Okay. So coming to problem number 2. So in problem number 2, they are telling you to find out the correct product of the reaction. So now again you have to find out the product of this reaction. So you have to find out the product. So what is the condition? They have taken a aldehyde, a acid anhydride, anhydride, and they have treated it with sodium acetate in presence of heat. So now what will happen? Sodium acetate is a acid or a base? What it is? It is a acid or a base? Base. So sodium acetate is a base. So that is why now it will, what a base will do in this reaction?
Abstract a proton.
Yeah, abstract the acidic proton. So which proton it should abstract? Which is the acidic proton here? So So it will abstract the proton of this,
Anhydride.
yeah, anhydride. This particular proton is getting abstracted from this carbon, and you are getting a negative charge generation at this position, the alpha position of the carbon. Okay. So why it is acidic? Because this negative charge, when
From
it,
conjugation.
yeah, it is in conjugation. Whether if you abstract a proton from there, it is in conjugation, but you have a oxygen with lone pair of electron as well. So it will destabilize that negative charge because of the conjugation. Okay. So there would be a electronic effects, electron crowding at the alpha position because of the lone pair that is free on oxygen. It will participate in delocalization and makes the alpha carbanion to aldehyde less stable, that is destabilize it. Okay. So that is why instead of deprotonation of this alpha proton, it is deprotonating this particular proton that is more acidic than this. Okay. So after abstraction, now what it will do? A carbon ion is getting generated, a nucleophilic center is there. Now, can anyone tell me what it will do now? What is happening next? So, this carbon ion will, as you can see here, it is a aldehyde group, right? This is this group, no? So, here the anion is getting generated, and after that, as you have a nucleophilic center here, but electrophilic center is also present in the reagent, that is this carbonyl carbon. So it will attack to carbonyl carbon and give you this alcohol. So after getting this alcohol, now what they have did, they have heated it. So after heating, what will happen? This dehydration will happen, and also there would be a cleavage of this particular group. So where from where it would cleave? It would cleave from this side. So there would be a cleavage of this acetate, and then you will get a alcohol because of the heating. As they have mentioned in the reaction condition that in the second step they have heated the reaction. So that is why after heating, dehydration is the step which is going to take place. From this side, this OH and H is leaving. So what is happening? This H goes here and this OH leaves out. And this breakage of the carbon oxygen bond will take place to give you this acid. That is the alpha beta unsaturated acid. So in this case, you will get this because of the heat that is mentioned here. You are getting the cleavage of this CO bond. So that is why instead of getting a whole side chain, you are getting only the acid. So is it understood, guys, the mechanism of this reaction? Why the alpha hydrogen is getting from this, not from the alpha position of the aldehyde? Is it clear? Is it clear? Should I move forward or should I explain it again? Any doubts?
No, ma'am. Move forward.
Okay. So the correct option will be option number 2. Okay. So coming to problem number 3 now. So in this, you have to find the product of the reaction. So they have given you 2 into this substrate. So this is the reactant. So they are telling you that you have 2 equivalent of this orthomethoxyaldehyde, and they have treated it with KOH, that is a base. So can anyone tell me what will happen in this reaction first? This is a base, KOH is a strong base. What did KOH will do now?
It may abstract a proton.
Okay, so from where do you think the abstraction would takes place? Is there any acidic proton which is present in the reaction within the substrate?
Aldehydic group, ma'am.
No, actually, it cannot abstract this proton because it is not the carbon, na?
Okay, yes, yes.
Yeah. So it cannot abstract this aldehydic proton. This is not a ketone, this is aldehyde, so it cannot be abstracted. So this is not a alpha proton, and
Yes,
as you can see here, there is no acidic proton which is present in the system, right? So now what will happen? Base has no choice of abstraction of proton. Now what? How it will act now? It will act as,
Canizaro's reaction.
sorry.
Canizaro's reaction.
Yeah, it is a Cannizzaro reaction. Very nice. So here,
What?
what will happen? Instead of abstracting the proton, base will react as a nucleophile because it has no choice but to act as a nucleophile. Because it is a strong base, it can either act as nucleophile, either abstract the acidic proton. So first choice of base is to abstract the acidic proton if there is any present in the system. But as we can see here, there is no acidic proton that is abstractable. That is why KOH, instead of acting as a it's as a base which abstract a proton, it will act as a nucleophile. Okay. So in our case also, KOH will act as a nucleophile. And someone has said this is a Cannizzaro reaction. Very nice, because when you have no alpha hydrogen present in the system and you have treated it with base, then instead of aldol, what works here? It is a Cannizzaro reaction. If you have a alpha proton at this position, then you can simply say a aldol reaction is taking place, right? So we will abstract a proton from here, carbon ion get generated, and then this carbon ion will again react on second molecule of the similar compound, right? That is known as a aldol reaction. But if you have no alpha proton that is present in the system, then the reaction is known as Cannizzaro reaction. So how the mechanism goes? So first of all, base will attack on the carbonyl carbon as a nucleophile and then will form a hydrate anion. After that, again the second molecule of base will abstract a proton from OH, generating a dianion, and this anion will attack to the second molecule of this benzaldehyde. So here this anion will attack onto the second molecule. So what will happen? This anion goes down and there is a hydrogen shift that is taking place to this carbonyl carbon. Basically, this is the hydride. This is not the hydrogen ion, this is the hydride. This is H negative, which is getting displaced to carbonyl carbon. And then what will happen? This will generate you alcohol, and this, the part which is there at the dianion, after coming down, it will generate a carboxylate anion which takes up a proton from the system and generate carboxylic acid. So what will happen here? A aldehyde is converted into an alcohol, corresponding alcohol, and corresponding carboxylic acid. So both the compounds are getting generated, a alcohol and a carboxylic acid from an aldehyde. Okay. So what is, again I'm explaining the mechanism, guys. So what will happen here? First of all, base will attack onto the carbonyl carbon, that is the electrophilic center. Then a hydrate anion will form. Then base will abstract again the OH proton and a dianion is getting generated. After coming down, this hydride shift is taking place. The key reaction of this reaction is this hydride shift. So this hydride is shifting to the another molecule of the same type to give you a alcohol and a carboxylate anion, which will take up a proton from the system and generates a carboxylic acid. So, is this mechanism understood to all of you? Just take up a look on it. Is this understood? Is it clear, or I should repeat it?
Yes, ma'am.
Okay. So if it is clear, then coming back to our question. So now can anyone tell me now here what would be the correct option? Just do
C
the
will be
maths.
correct.
C option. Okay. Any other answer than this? Yeah, it is very much clear that aldol condensation is not going to happen. That is why it is getting rejected, because there is no alpha proton which is present to get the aldol product. That is alpha beta unsaturated ketone. The product we get in aldol condensation, right? And here also in the second option, there is a aldehyde and a alcohol. So I have told you we have generated the corresponding acid and alcohol. So third option having the acid and alcohol, fourth is having a alcohol and aldehyde again. So the third option is the right one. We are generating the corresponding acid and alcohol of this particular aldehyde. Okay, so whenever you have a strong base in the mixture and you don't have any alpha hydrogen or acidic proton that is present in the system, then base has no other option but to act as a nucleophile. So it will act as a nucleophile and then directs the reaction. Okay, so is it clear, guys? The mechanism of this reaction, the reasonings, the logic behind it? Is it clear? Okay, if it is clear, then I'm moving forward. So in problem number 4, they are asking you to identify the major product of the given cross aldol condensation. So they have told you that this is a cross aldol condensation. What do you mean by cross aldol condensation? See, aldol condensation could be of various type. Cross aldol means you have two different reacting species. If you have a same reacting species, just think about an acetone reacting with acetone. Acetone, what is acetone? So this is acetone. So if you react acetone with another molecule of acetone, that is 2 into, then you will say that it is a same aldols condensation, similar. So it is a similar aldol condensation. But when you have different reacting species, instead of two molecule acetone, you have one another species, one acetone, one acetophenone. Then you will say that yes, it is a cross aldol condensation. Okay, so aldol condensation taking up between two different reacting species, then we will call it as a cross aldol condensation. So now coming back to question, they are telling you to identify the major product of the given reaction. So you have to identify the major product. So what is happening in the reaction? They have treated this ester, diester, with this aldehyde in the presence of secondary amine and acetic acid. So they have treated it with secondary amine and acetic acid. Okay. So now can anyone guess what this secondary amine will do? Any guesses? So this secondary amine. So guys, you have the lone pair of electrons present on the amine. Okay. So now amine will react first to that carbonyl carbon that is electrophilic in nature, right? I have told you as it is a nucleophile, it will preferentially act to the electrophile. So now tell me which is the among these three, which is the more electrophilic carbonyl carbon? Anyone? among these I have asked you, among these three, that is 1, 2, 3, which is the more electrophilic carbonyl carbon to which this secondary amine should add, as it is a nucleophile, right? So which carbonyl carbon? 1, 2, or 3? Guys,
1, 2,
sorry,
1 and 2.
1 and 2. Okay. So one by one we will see which is the more electrophilic carbonyl carbon. See guys, what is happening here? So I have told you what two, 1, 2, 3, among these 1, 2, 3, which is the more electrophilic. So here, as you can see, this 1 and 2 have the same reactivity. So same reactivity, that means you have to choose between this 1 and 3, not 2, because these two are symmetrical, right? So because of the symmetry and also the nature of this ester group is similar. So I have told you in the previous lecture that this oxygen lone pair is in conjugation with this carbonyl carbon. Similarly, here also this lone pair is in conjugation with this carbonyl carbon, right? Which is making this carbon less electrophilic in nature. Why? Because there is a double bond character which is developing between CO bond. So there is a partial double bond character that is developing between the CO bond in both the ester species. That is why it is less electrophilic with compared to aldehyde, because there is no such kind of conjugation that is present, and this carbonyl carbon is more electrophilic than this one. So the those who have taken the previous lecture, I think the lecture 4, in which we have talked about these kind of questions of electrophilicity and nucleophilicity, they have told you that esters have lower electrophilicity than aldehyde. Okay, so aldehyde are more electrophilic than ester because of the resonance. So there is a delocalization which is present in ester, which is making the carbonyl carbon less electrophilic than aldehydes. So now tell me at which carbonyl carbon this prime secondary amine will attack?
Third.
Yeah,
Third.
yeah, because it is more electrophilic in nature. So it will attack to this. Now after attacking, what it will form? So there is a N. I'm just keeping R2 as this. So here there will be H, and here there will be OH. Fine. These are two methyl groups. So this is what it is forming. So now after that, what will happen? This H, it is positive. So now you have to form a enamine between this. So here, after the removal of water molecule, what will form? So basically there is a double bond which is getting formed between this carbon and nitrogen. So this is this. Fine. So basically they are activating your aldehyde. So this is a simple thing to activate aldehyde. So it is activating your aldehyde, and now what will happen? It is making it more electrophilic than it was previous. So in this aldehyde case, this carbonyl carbon, the electrophilicity now drops after the formation of this enamine. So this imine formation drops your electrophilicity, sorry, increases the electrophilicity of your carbonyl carbon than it was previous. Okay. So the main purpose was to activate your aldehyde for the nucleophilic attack. So now electrophilicity of your carbonyl carbon is increased when you have formed the imine. So now again you have this particular ester group which is present. So now again what will happen? After the formation of imine successfully, the second substrate has to impart the nucleophilicity because you have made one fragment as electrophile. So this is the particular electrophile. So the second fragment has to be a nucleophile for the reaction to happen, right? So now tell me, in the first compound, that is this diester, which is the nucleophilic site, which is the nucleophilic site, or simply which is the acidic hydrogen.
Methylene group.
Is it alpha hydrogen or beta hydrogen? Because the molecule is symmetrical, so both are beta. So tell me, which is the more acidic hydrogen, alpha or beta?
Alpha.
Alpha hydrogens. Very nice. Because now, as you can see here, in this case, after the removal of alpha hydrogen, the carbon ion that is getting generated over here is highly conjugated. It is in conjugation with this particular carbonyl and this particular carbonyl. So it is highly conjugated. So because of which the hydrogen that is present at alpha is becoming the acidic hydrogen, and these kind of species are known as active methylene compounds. What did you mean by active methylene compounds? That this methylene group, that is the methylene group, which is at the alpha position, this is the methylene group, right? We say it as methylene. This particular group is methylene group. As these are methyls, this is methylene. So active methylene means the methylene group is highly active in those compounds are known as active methylene groups. So basically the methylene at alpha position of these compounds are highly reactive, highly activated, that the hydrogens are so much acidic that it can act as a nucleophile in this particular system. So this alpha position of these active methylene groups are very much nucleophilic in nature, and that is why here your aldehyde is becoming the higher electrophilic nature. And now after the generation of the carbon ion at the C alpha position, this nucleophile now will attack onto your electrophile. That is the imine which you have formed by the attack of secondary imine. So now what will happen, guys? Now you will have a formation of imine over there with this R groups, and this is the active methylene compound. That means this methylene group is highly activated, which means you can generate a carbon ion at this position. As the hydrogens are highly acidic, so it will behave as a, sorry, anyone wants to say something? Okay, so now it will act as a nucleophile and it will attack to your imine to form this compound. Basically I have, anyone wants to say something? Please switch off your mics. Can you please switch off your mic? Whose mic is on? Okay, so now this carbon ion will attack onto the imine, and here you will get a nitrogen, okay, with R groups. So this is what you will get after the nucleophilic attack, okay. So now, as a dehydration step will takes place, you can also remove this particular group as again R2NH. Now you will generate a R2NH in the system again, from which you have formed a imine. The precursor is ready to remove, because here also you have R2 attached with this nitrogen without hydrogen. Basically hydrogen is not there, so there is a dehydrate. As a dehydration step is taking place, similarly this step is taking place to remove this R2NH, that is a neutral species, which is a driving force of this reaction. So the dehydration step has a driving force of removal of the neutral species, that is water molecule. Here also the similar concept takes place, and your neutral molecule is removing, that is a secondary amine, to give you this alpha beta unsaturated ketone. So here the driving force is the removal of the neutral molecule, as well as the generation of a more delocalized system, that is alpha beta unsaturated esters. So that is why it is getting removed. So this is how you will get to the product. So now tell me which is the correct option among these four.
A is the right answer.
Yes, A is the right answer. So is it understood, guys? Is it clear? Okay, if it is clear, then I'm moving forward. This is also a very simple question on the similar line. So they are asking you what would be the major product of the following reaction. So you have to answer the reaction product. So they have taken 2 into this cyclopentanone, that is the 2 molecule of cyclopentanone. So can anyone tell me which is this reaction basically? Actually, they have mentioned it as KOH. The reagent is KOH, that is a base.
Aldol condensation reaction.
So this is a aldol condensation reaction which is happening between these two substrates. Why aldol condensation? Why not Kenizero? Because here you have the alpha hydrogens that are present in the system. So here you will abstract a proton from the alpha position of the cyclopentanone, and the carbon ion that is getting generated will attack onto the next molecule of the cyclopentanone to get you the compound. So can anyone solve this and tell me which is the correct option among these four?
A is the right answer.
Yes.
First one.
Yeah, first one is the right answer. So what is happening here, guys? So first of all, the carbon ion getting generated. This is attacking onto this carbonyl carbon to get you this alcohol. After dehydration, that is the aldol condensation. Condensation means the removal of water. So here, after dehydration, you are getting this molecule generated. So option number one will be the correct answer. So is it clear the mechanism of this reaction? Okay, if it is clear, then I'm moving forward. So in problem number 6, they are asking you for the sequence of reaction shown below. You have to answer compound A is a lithium enolate. So you have to basically find out which is the correct statement among these four for the reaction that is shown below. So before answering, you have to figure it out with what is A, what is B, because they have commented on A and B and steps of the reaction. So you need to know what is A and B, and then you can answer this question. So first, I have told you whenever you see zinc and CBr bond, there is a oxidative insertion between the CBr bond, and as a, what you will get? You will get this product, zinc coordinated with Br. Fine. So A is this species. Basically, I have drawn it. So A is this species. So A is equal to this. So in first option, they are saying you compound A is a lithium enolate. Is it a lithium enolate? Tell me, is it a lithium enolate, guys? The compound A?
No.
Yes. So it is not a lithium enolate, as I have mentioned in the previous lecture of enols and enolates, that what is meant by lithium enolate, how you will form a lithium enolate by reacting species that is having a alpha hydrogen, that is a highly activated carbonyl compound with LDA, then you can form a lithium enolate. So here this is not a lithium enolate, so this option is the wrong one. Okay. So now they are commenting on second step is benzylic acid rearrangement. Compound B has two aromatic ring. Compound A has two aromatic rings. So now again they have commented on compound A, that is this compound. So it is having two aromatic ring. So it is having only one aromatic ring, right? Over here. So that is why we can also say that this option is also incorrect because compound A doesn't have two aromatic ring. Instead it has only one aromatic ring. Fine. So now for solving this, you have to answer B compound. So after the formation of A, they have treated with benzaldehyde and water. So if I treat it with benzaldehyde and water, then what will happen? So here is the answer. So here this is A. You have treated it with benzaldehyde. So this is the structure of benzaldehyde. So if you are treating it, I have told you that the adjacent carbon of the zinc Br bond is nucleophilic in nature. So it will act as a nucleophile onto your carbonyl carbon of benzaldehyde to give you oxyanion generation, which trap the proton from the water. So this is what you will get as a B. So this will be the B product. So here in the first step they have treated with benzaldehyde, second step they have treated with water, which means they have treated it with benzaldehyde up to here, oxyanion generation. After that treating with water will abstract a proton and will give you an alcohol. So this is the B compound. So this is the B compound. So, so coming to the question, the second part, they have told that second step is the benzylic acid rearrangement. So guys, is it a benzylic acid rearrangement, this mechanism? Anyone knows what is benzylic acid rearrangement? So if you don't know, then I have a slide for you, that is this. Basically, when you have a diketone in the system, na, adjacent diketone, this kind of system, you have this adjacent diketone and you treat it with base NaOH or KOH, then it will act as a nucleophile. I have told you that it doesn't have alpha hydrogen, then the nucleophile, that is the base, will act as a nucleophile rather abstracting a proton that is acidic. So it doesn't have a alpha proton that is acidic, that is why it is behaving as a base. Now it will get generate this oxyanion. There is a migration that would takes place. So migrating OH and migrating phenyl, you have a two options. That means here migratory aptitude of phenyl is higher, that is why phenyl is getting migrate towards this carbonyl carbon to get generated with this acid, and you have this oxyanion which will take up the proton and you will see the formation of a alpha hydroxy acid. So basically this is the alpha hydroxy acid that is getting generated in benzylic acid rearrangement. So as the name suggests, acid is getting formed in the reaction mixture from diketone. So this is what benzylic acid rearrangement looks like. So can anyone tell me, is it the benzylic acid rearrangement which is happening in the second step of this particular reaction?
No.
No. So it is not going to happen. This is also the wrong answer. So now the third option is the compound B has two aromatic rings. So is it the right one or not? This compound B has two aromatic ring. Yes, one and two. So you have two aromatic ring in the compound B. That means option number C will be the correct one. So again, I am going through this sequence of reaction. See what is happening in the first step. You will form a reformetsky enolate rather than the lithium enolate. See, this is how you will form a reformetsky enolate. This C zinc enolate is known as reformetsky enolate. So zinc will donate the lone pair to this carbon. This bromide will leave out, and this bromide again attacks on the zinc to form this zinc Br enolate. This is how the zinc is coordinatively oxidatively inserted between CBr bond. So this is what is happening in this particular reaction. So it is not a lithium enolate. In the second step, what is happening? Benzaldehyde is getting reacted with this to get you this oxyanion, and after that hydrolysis takes place to get you alcohol. The benzoic acid rearrangement is a rearrangement having the adjacent diketones. When you treat it with a base, it will act as a nucleophile. Then there would be a migration that is happening, and after that, the protonation will give you the alpha hydroxy acid. So, this is how the benzoic acid rearrangement takes place. So in this compound, compound A is not a lithium enolate. Second step is not benzylic acid rearrangement. Compound A has only one aromatic ring, but compound B has two aromatic rings. So option number C will be the correct one. So is it understood, guys? The problem number 6.
Yes, ma'am.
Okay. So moving forward with problem number 7. So it is on the similar line which I have explained previously about the amine. So they are saying that structures of intermediate P and the major product Q formed in the following sequence are. So they have given you four options having P and Q structures. So you have to tell me that which is the correct one. So can anyone tell me which is the correct option for P among these four? This is on the similar line which I have explained previously. The formation of imine takes place, right? Then what will happen? Think about it. See here, it will go like this. Fine. So what you will get here? You will get a, basically I'm writing the core. You will get this nitrogen with this five membered ring, and there would be a methyl. Fine. There should be a positive charge on nitrogen as well. Okay, so this is what you will get after treating this ketone and amine. That is the secondary amine. So they have formed enamine. So from which side enamine will form? Either from this side. How the enamine forming? So this hydrogens basically. I have told you that this nitrogen being electronegative in nature, it doesn't prefer to have the positive charge with it. That is why to neutralize positive charge, you have to give it a stable conformation. And what is the stable conformation? Sorry. So the removal of proton from either of the side, it will go like this and it will neutralize. So alpha proton can also do that. Sorry, alpha 1 or alpha 2. So what do you think? Which kind of enolate will form? From alpha 1 or alpha 2? Which is more stabilized?
Temperature is high, so more substituted side.
Okay. So now what is happening? Reflux temperature, fine. Thermodynamic product will form, fine. But that concept lie with the kinetic and thermodynamic enolate. But the thing here is you have a generation of negative charge, right? So negative charge is getting generated over here, alpha position. But enamines have some different kind of stability and conformation. That is why it doesn't prefer the rules which is applied on the enolates, that is lithium enolates basically. So enamine doesn't follow that rules. So here what is happening, you have to have a negative charge at this position, right, and negative charge at this position. So which negative charge is more stabilized? alpha 1 or alpha 2? Tell me guys, which is more stabilized, alpha 1 negative charge or alpha 2?
Alpha 1.
Alpha 1. Yeah, alpha 1 because it is a secondary carbocation, right? Carbon ion, sorry. So that is why, so here additional methyl will give you the less stability of this particular carbon and that is getting generated. So that is why the preference which will be here is for the formation of this enamine. Basically abstraction of the proton from this side, and it is going here, and there will be this double bond which is forming in the system rather than the more substituted side double bond. Okay, so here this is what it will be. So this is the enamine which is getting generated. This positive charge also get neutralized. Okay, so this is what you will have generated. So this is the compound P. So now tell me what is the compound Q. Tell me which is the correct option among these four.
C is the correct option.
Okay, C is the correct option. Yeah. So what is happening here? See this positive charge is neutralized, so this lone pair is present there. So it will come down. It will attack onto your this carbon. It will leave out, and after hydrolysis, your enamine, which is your amine, which is getting a positive charge here now, will get hydrolyzed to give you a ketone. So in hydrolysis condition, this imine hydrolyzes to give you a ketone. So all the rest is similar, but this imine is converted to ketone. So is it fine, guys? Is it clear the mechanism of this reaction? Okay, so if it is clear, just answer me. Now, if it is clear, then I am moving to problem number 8. So in the problem number 8, they are asking you in the reaction the products X and Y are respectively are. So basically, you have to find these X and Y. So they have treated this paramethoxybenzaldehyde and formaldehyde with concentrated sodium hydroxide. So what will happen? So can anyone tell me what will happen? What is this reaction? Tell me what is this reaction? You have just named it previously. They have treated it with a base. There is no alpha proton that is present in the system. So what it will do now, the base, what it will do? Okay, okay, I think you should respond to it. So here what is happening, guys? There is a base which is present. There is no alpha
A.
proton. Yeah, base is acting as a nucleophile. So base has to act as a nucleophile because there is no alpha a proton that is present to do the aldol condensation. So now aldol condensation is not operative. So which reaction is operative here?
Canizaros.
Yeah, Cannizzaro reaction is operative here because there is no alpha hydrogen is present to abstract. So here also on the similar line, NaOH will attack to this particular aldehyde. So which aldehyde is to be attacked? This aldehyde or this aldehyde? Which is more electrophilic? Formaldehyde or benzaldehyde? At least this you need to know. Which is more electrophilic carbonyl carbon? Formaldehyde or paramethoxy benzaldehyde? Any guesses? Just tell me now. It should not to be like it should not be correct all the time. You just have to make a guess or something.
Benzaldehyde.
Yeah, benzaldehyde. Okay, so I'll brush it up. So guys, what is happening? I have told you. I have basically asked you what is more electrophilic in nature. Okay, so this is formaldehyde. This is benzaldehyde. So is there any delocalization which is present in this case, formaldehyde? No. But
No delocalization.
yeah, as you can see here, this is paramethoxy. So it is giving electrons in the ring. Again, it is in conjugation with this aldehyde. Again, this COCH, basically CC bond is this CC bond is having a partial double bond character. That is why, due to the localization, it is it is decreasing the electrophilicity of this carbonyl compound rather than formaldehyde. So formaldehyde is more electrophilic than benzaldehyde. Is it clear now? Is it clear why formaldehyde is more electrophilic than benzaldehyde?
Yes, yes.
Yeah. So just keep these things in mind. Why delocalization is playing important role. What is affecting the carbonyl carbon? So whenever you see delocalization with carbonyl carbon, then you can say yes, a double bond character is getting generated between CC bond. That is why the carbonyl carbon is not electrophilic now, that much electrophilic now, which is previously it is. So here formaldehyde is more electrophilic, so OH minus will attack to that particular group. Now if attacking will takes place on the formaldehyde, then what will happen? This will give you this. Fine. Again a dianion is getting formed, right? Which I have showed you previously in the mechanism. So if this is hydrogen and this is also hydrogen and you have benzaldehyde in the system, then this hydride shift will take place. So this hydride will attack onto this particular group, and what will get generated? What would be generated? At least now tell me the right option. And you have a alcohol over there, right? So there should be a, sorry, alcohol that is present on this. And this is paramethoxy, right? I have the chemtron. Okay. So this OH minus will attack onto it. This will come down. Basically, this dianion is getting formed. This will come down, and hydride will get shifted towards your paramethoxybenzaldehyde to give you this formic acid and benzyl alcohol. So if you don't know that which is more electrophilic between benzaldehyde and formaldehyde, then you will confuse with all of these options, and you will surely suggest that yes, this particular aldehyde will form a acid rather than the formic acid formation. So first of all, in the Cannizzaro reaction, you need to know which is the more electrophilic center at which base has to attack, where should be the dianion form, and how the hydride will go on another carbon. So is the mechanism understood to all of you? Any doubts, any queries in this particular mechanism, guys? Any questions? Speak up. Am I audible?
Yes, ma'am.
Okay. So now tell me the correct option.
B is the right answer.
Yes, option B is the right answer. So basically, in the Cannizzaro reaction, you first need to know the electrophilicity of your starting materials. Okay. So this is how you will solve a Cannizzaro reaction cross problem. So coming to problem number 9. So they are telling you to find out the major product form in the following reaction. They have treated it with base, that is KOH, in methanol. Now quickly tell me what is the answer of this reaction. I have previously taken up this particular question. So tell me what is the correct option.
C is the right answer.
C is the right answer. Okay. So first of all, you have two possibilities, right? Whether this base will abstract this proton, as this doesn't have, and this is the quaternary carbon, right? So it has two options, either this or either this. So if it abstracts a proton from this side, then you will have how many number of carbon ring? One, two, three, four, five,
Seven.
six, yes, seven. Then you will have seven membered ring, right? I missed something here. No, no, okay. So you will have a seven member, sorry, 78. You will have eight member ring, because it is starting from here, na? From this carbon to this particular carbonyl carbon. Attack will takes place to this carbonyl carbon. So it either you will have eight member ring if the negative charge is on this carbon, that is this carbon, then you will have one, two, three, four, five, and six. Then you will have a six membered ring. So you have two possibility, either to form a eight membered ring formation or a six membered ring formation. So two possibilities are there. So first of all, just tell me which is more stable ring, six membered ring or eight membered ring. If there is a preference of formation of six or eight, which is forming earlier, which is forming the fastest, six or eight, thermodynamically, which is possible. So let me tell you,
C.
yeah, six. So let me tell you, the six membered ring formation, the rate of formation of six membered ring is faster than rate of formation of eight membered ring. Okay. So six membered ring, because it has a higher stability, it has a higher chance to form. So in this question, basically, the OH minus will abstract a proton from this side. So so as to form the six membered ring. So six membered ring formation will take place, and after that the simple dehydration step will take place to form the alpha beta unsaturated ketone. So this is how you will get the alpha beta unsaturated ketone formation. So yes, option number C will be the right one. So is it understood, guys?
Yes, ma'am.
Okay, fine. So coming to problem number 10. So in the problem number 10, they are write the correct order of reactivity of benzaldehyde given below to give the aldol product in the presence of sodium hydroxide. So basically, they are treating this benzaldehyde in aldol condensation reaction, and you have to answer which of these four benzaldehyde will react faster with this benzaldehyde to give you a cross aldol condensation product. So you have to react this benzaldehyde with this substituted benzaldehyde, and you have to find out the correct rate, reactivity order of the benzaldehydes given. So can anyone tell me what will be the correct rate? Just go to the concept, go to the basics. What is happening in the aldol formation, aldol product? So is there any alpha hydrogen which is seen in these particular benzaldehyde? Is there any alpha hydrogen in this benzaldehyde in all the four? No, right? So this benzaldehyde doesn't have any alpha hydrogen. So they are saying that if I react this acetophenone with sodium hydroxide, then which of these benzaldehyde will react faster with it? So what they have done is the sodium hydroxide being a base, it will abstract the alpha proton. So acetophenone has a alpha proton, right? So carbon ion is getting generated here, and this is going in a delocalization, right? So after the generation of carbon ion, now it has to act on a electrophile. So benzaldehydes are behaving as an electrophile here. So these four are electrophiles. So now tell me the correct order of this electrophile to react with this nucleophile. So higher the electrophilicity, higher will be the reactivity of that particular benzaldehyde, right? So just tell me which is more electrophilic carbonyl carbon in these four, which is the most electrophilic carbonyl carbon.
A,
A. Okay. After that,
C,
okay. After that,
B, and D.
yeah. So this is how you have to think about it. So here they have already given you that yes, just they have tricked you that we have taken acetophenone with sodium hydroxide and these are the benzaldehyde. Now you have to identify the correct order of reactivity. What do you mean by reactivity now? Here after the generation, as you can see here, benzaldehyde cannot give you alpha proton, so a carbon ion cannot be generated out of it. But acetophenone can generate a carbon ion, so it is the species which is behaving as a nucleophile, right? So benzaldehydes are the electrophile here in the aldol condensation reaction. So now, if you know that it is an electrophile, then higher the electrophilicity, higher will be the reactivity of that electrophile. So this is how you need to think about it. So here, as you have said, A will be higher reactivity, then C, then B, and then D, because this is a nitro group which is attached here. It will make it more electrophilic by electron withdrawing group. Then there is no substituent. Then methyl is there, which is a little electron releasing group. Okay, but methoxy has a higher strong electron releasing power. That is why it is at last. So it will make your carbonyl carbon very less electrophilic in nature. So that is why, which is the correct option, guys? Option number
D, option
option
number D.
number D. So A, C, B, and D. So here option number D will be the correct. Okay. I hope all of you have understood this concept. So coming to problem number 11. So in problem number 11, they are asking you what is the order of enolic content of this particular esters, ester, ketone and aldehyde. So this is your ester, this is your aldehyde, sorry, ketone, this is your aldehyde. So now you have to find out the enolic content. What do you mean by enolic content? So here I have just focused on these particular conformations. So this is your one, this is your second option, and this is your third option. So what do you mean by enolic content is how many alpha hydrogens you have to form enol. So we have talked about enol and enolates that they are tautomer. Keto and enol form are tautomer of each other, right? So enol content means how many alpha hydrogen can be abstracted from the system to form alcohol here. Just suppose if we consider this first compound, this is this can be generated a carbon ion. This is the alpha proton, right? Now this is also having a alpha proton at this side. So these two can go in conjugation and can form a different structure. That means you have to form different resonance resonating structures for this particular species. So how many resonating structure can be formed out of it? Measure the number of resonance structure that you can make out of it, higher will be the enolic character. So higher the conjugation species, higher will be the enolic character. So first it can form here. The second option will be you can, instead of from this alpha proton, you can form the enol from this side, right? First side is this, second side is this. Is it right? Is it understood? Guys, is it understood how you have formed two resonance structure, that is two enol form of this particular diketone? I'm just asking about one. See, I have told you that enolic content means that how many possible alpha hydrogens you can remove from a system to generate the resonance species, that is the alcoholic species of that particular diketone. So we have abstracted two alpha proton, that is the alpha proton which is present in the system. Two alpha protons are only protons that can be abstractable from the system in the case of one. Okay, and you can write two possible resonance form and in that case fine. And the third one you can also write that you can also write this structure. Don't touch this ketone, you can form enol from here, right? This is oxygen, this is again ethylene. So three possible resonance form are possible for this part one. So is it understood, guys, this much? Okay, so if it is understood, then coming to this part 2, how many alpha hydrogen now this compound have? How many alpha hydrogen does this compound have? Part 2. At least respond now so that I can know that yes, you people are aware what is happening here. So these are three alpha hydrogens, and if you write the resonance structure for this particular compound, it will be coming out higher than this particular diester and this one ester, one ketone and one aldehyde form, because you have again 1 and 2 alpha protons over there. similar to this case, but if you write the resonance form, then you get to know that this particular aldehyde enol form has more resonance structure than this ester. So please go and write the resonance form of each of these three, and you will find that the higher enolic content is there for this diketone because of the presence of higher alpha hydrogens, as well as the resonance structures are higher in number. So when you compare part 1 and part 3, then you will realize when you write the structure that even though they have two alpha hydrogens, but the resonance structure for this particular species is higher and stable than this species. So this is how you will find out the enolic content. So here the enolic content will be highest for this diketone, which is then this particular aldehyde and then this particular ester. So you will have second as a higher enolic character, then third, and then first. So the correct option will be the second will be higher, then third, and first. D part will be the correct one. So is it clear, guys? Any doubt, any queries in this question? Please respond.
Yes, ma'am.
So just try practicing this question. Okay. Okay, if it is understood, then we are moving. Okay, fine. So problem number 13. So which is not a reactive methylene compound? So I have told you which is the reactive methylene compound. If you have a diketone having a middle methylene compound that is present, and this particular methylene compound is higher in acidity, then you will say yes, it is a reactive methylene compound. So basically you need to have a system like this. If you have a methylene that is in bridge with this particular diketones, and these diketones will having a higher electron withdrawing behavior, that means if you have this methyl that is a diketone group, it is a electron withdrawing group, right? So that is why the two electron withdrawing groups are present. So this methylene is sandwiched between these two electron withdrawing group, which makes this methylene an active methylene compound, which can easily donate the H plus and will generate a carbon ion. So this is the particular concept behind this. So they are telling you you have to find among these four which is not a reactive methylene compound. So I have drawn the structures. So this is 1, 2, 3, 4. So now can anyone tell me which is not the reactive methylene compound among these four?
Fourth one is not reactive.
Yeah, fourth one is not the reactive methylene compound. Why? So guys, I have told you when you generate this carbon ion, it is highly conjugated and it is highly stabilized, right? So that is why it is a active methylene compound. Here also this negative charge in conjugation with this, and also in the nitrile. So nitrile having a triple bond in the system, so that is why it is in conjugation with this nitrile. Here also this is the highly active methylene compound, but when you generate carbon ion over there, it is in conjugation with this, but it is not present in the conjugation with this amine, right? There is no conjugation in the left side. So that is why we are saying that it is not an active methylene compound. So for active methylene compound, that methylene hydrogen, that is a carbon ion, should be in conjugation with that two diketones. So basically there is a requirement of having two electron withdrawing group which is present at the center. So there should be two electron withdrawing group, and a methylene is sandwiched between that two electron withdrawing group. So Cn is also an electron withdrawing group and CO2 is also an electron withdrawing group. So this methylene is sandwiched between these two electron withdrawing group. But when we talked about 4, then it is an electron withdrawing group, but this is not an electron withdrawing group. This is amine is not an electron withdrawing group. So that is why we are saying that it is not a reactive methylene compound. So, which is not a reactive methylene compound, guys? Which option is right? Option number. So, D option is the correct one. Okay. Now coming to problem number 13. So, which alcohol is the main product of base catalyzed reaction of epoxide 1 in methanol? So, you have to just identify the alcohol. So, there is a epoxide opening by methanol, which is base catalyzed. That means methanol, if it is base catalyzed, then it is present as a methoxide anion, right? Because methanol hydrogen is abstracted by base, so there is a methoxide which is present. So now, if this methoxide has two positions to attack, either this or either this. So which is to be attacked? One or two. Which it would favor? Which is operative pathway, guys? Can anyone tell me?
First one.
First one. Why? Because it will attack to less hindered side. See, guys, here acid to reaction mechanism is operative, so that is why methoxide will prefer a less substituted site to attack on, and this will generate you alcohol. So, which is the correct option now? Option number
D.
D. Why? Because the epoxide opening will be anti, right? Methoxide will attack from downside because the epoxide ring is on above the plane. So it will attack to down the plane, and the epoxide opening will take place from above the plane. So this is what it will form. So coming to problem number 14. So in this, in which of the following equation is the main product wrong? So you have to identify which is the wrong product. Okay. So one by one we will see the reaction and we'll identify which is the wrong product. So in first case, cyclohexanone is reacting with bromine acetic acid to give you this alpha bromo cyclohexanone. Cyclohexanone. Is it right or not? Is this particular reaction correct or not? Can anyone tell me the outcome is right or not? See, acetic acid will protonate this, right? Whenever you have a acid, it will protonate your carbonyl oxygen. If it protonates, as you can see, this hydrogen is acidic now. So if this hydrogen is acidic, then it can go here and can neutralize the positive charge on your oxygen because it is an electronegative atom. It cannot bear the positive charge, right? So what you will have here is a OH with internal double bond, right? So after formation of OH with internal double bond, now what will happen? Your oxygen has lone pair of electrons. So after formation of OH here, your oxygen has lone pair of electrons. Now this CO bond is a single bond, right? So you have a lone pair of electrons on it. It will come down. It will attack to your bromine atom. Br minus will knock out to give you this alpha bromo cyclohexanone. So is it clear how the mechanism is going? Now tell me, is it right or not?
Right.
Right.
So this particular outcome is right. Now coming to second outcome. Can anyone tell me, is it right or not? See, they have treated this acetophenone with sodium hydroxide, that is a base. So what will base do? So base will abstract a proton, right? So which proton is to be abstracted? This diol protons or this acetophenone methyl group, alpha position? Which will this base abstract? alpha proton 1 or this proton, second proton?
One proton.
Because of the conjugation that is present after the proton deprotonation, the carbon ion is in delocalization. That is why one proton has to be abstracted. So if it is abstracted, a carbon ion is getting generated over there. So now this carbon ion will attack onto your CH2. It will leave out your OH as OH2 plus because water is present. So it will protonate your one of the oxygen and you will leave out as H2O. So it will leave out as H2O. As you know that OH minus is not a leaving group, good leaving group. So that is why it will make your OH a good leaving group by removing water molecule. And now you will add up having this particular species. So now tell me, is it right or wrong outcome?
Right.
Yeah. So now seeing this problem number C. So here they have treated the symmetrical molecule with sodium methoxide ethanol. Now tell me, you can tell me now, is it right or not?
Right.
Yeah, because here also carbon ion is getting generated over there because it's a symmetrical species, no? So either here, either way is fine for this. So how many number of carbon will form a ring? One, 2, 3, 4, 5, and 6. So this OAT will leave out when your oxygen ion come down and you will find that this product is the only product which is getting formed. Okay. So this is also the correct outcome. So now coming to D outcome. So this, if you have, then you have a lone pair of electron which is present on nitrogen. So if you treat it with this allyl chloride, then they have told you that it will form it will form the allylation product at this particular species. How it is forming? It is going like this, then it is going like this. Cl minus will knock out. So is this particular alkylation possible? Why it is not possible, guys? Because enamines undergo alkylation mainly at the N position because this N position of enamines is highly reactive. So if alkylation has to be done, then it will directly go like this with primary alkyl halides. Okay, with primary alkyl halides, it will go directly on this. For the C alkylation, you have to be get a very reactive alkylating agents rather than the allyl halide. You cannot simply alkylate enamines with simple primary alkyl halides. So for this, you need to know how enamines reacts. So basically, this is a homework question for you guys. Study about enamines because it doesn't follow the rules which I have told you about the kinetic enolates and thermodynamic enolates. So there is some other rule which is governed for this enamines. Try to see how the reactions of enamines are going to happen. Okay. So we have a limited time, so we cannot cover all the reactions of enamine, all the behavior of enamine. So I have included 2 3 questions only. So if you go and read about enamine, then you will also find that there is certain limitation which is there for the alkylation of enamines. Okay. So here this particular species outcome is the wrong one. So D part is the wrong part. So is it understood all of you?
Yes.
Okay. So just read about enamines. Okay. It is the main concept. If you get it, then it is easy for you to understand the coming lectures also. Okay. So going to problem number 15. So guys, this would be the last problem of our today's tutorial. So what is this? They are asking you the major product form in the given reaction. So again, you have to identify the product. So now can anyone tell me what is the product? What is this reaction? The name reaction? What is the name of this reaction?
Aldol condensation.
Yes. So do the aldol condensation and tell me what will be the product of this reaction. So let me take up for you. Sodium hydroxide, extract proton from this particular side. It will attack onto the carbon and carbon of the another symmetrical molecule. Then it will generate this alcohol. After dehydration, you'll get this. So which is the correct option?
B is the correct option.
Yeah, option number A will be the correct one. So this is how the mechanism, this basic mechanism of aldol condensation is there. So I think it
Then,
is
ma'am, what is the difference between A and D?
A and B.
A.
Okay. So you don't basically they have abstracted a proton from this side and you are having basically there is a OH that is present here and they have dehydrated it. So if you just draw it now, you will find that it is not the correct disconnection which they have used here. So the dehydration step which they have done now, it is not at the particular right side. So for this to happen, what will happen? This will get generated, right? And to which this particular negative charge is getting attacked. If you are saying that it is getting attacked, yeah, but you can see that this is the particular dehydration site and they have dehydrated from this side, right? This is what they have done now. They have dehydrated from this and you'll get this right now. So the dehydration step is happening from their side. So this is not the particular thing. So here the exo methylene group that is present here, the exo double bond is much more present in the conjugation. If you place double bond here, then I agree it is in the conjugation with this particular benzene ring. But if you place here, then the alpha beta unsaturated ketone is there, and also it is in the conjugation with this. When it come down the oxyanion, then it also acts in the conjugation of this particular double bond. So this is highly stable than this particular species. So there is a competition between the stability of A and versus B. So if you compete this A and B, then you will find that
D option. D option.
sorry,
D option.
okay, D option. D is a similar one, na? So A and D are similar.
Okay, so both right
Ha,
answers.
both is the right answer. So B is the dehydration product from the different side. So that is why, if you consider it, alpha beta unsaturated ketone is the more stable species. That is why A is offering you the product, not the B. Okay. So dehydration is happening from the this junction rather than this exocyclic or sorry endocyclic double bond. So A option is the correct one. So is it understood now? Is it clear?
Yes, ma'am.
Okay. So if it is clear, then I'm just stopping the tutorial now. So this is it for today. So I hope you guys have gone through every question and you are clear with every answer. So thank you so much for joining the session. We will meet on next Friday, 6 to 8, with some other good questions. So thank you so much, guys, for joining the session.